This is chapter 5. It's on the concept of linear independence. I should say it's a little bit abstract and not that interesting, at least yet. On the positive side, I would say this. Actually, in this book, there is actually only one mathematical concept, and this is it. So the good news is you're going to see this. This is going to be, linear independence is going to be your friend for the rest of the book. And actually, hopefully later, it'll become clear what its importance is. But for right now, just consider this a first description of the topic. So linear independence. So we'll first describe what it means to be linearly independent, and then we'll talk about a related concept, a very important concept called a basis. So a set of n vectors, so here I'm using set notation, that's what those curly brackets mean, and this says we have A1 up to AK, and it's called, a set is called linearly dependent if there is a linear combination of the vectors that gives you 0. Now, of course, you can always make a linear combination of the vectors to be 0 if you take the coefficients betas, all the betas to be 0. That doesn't count, so it has to be a non-zero set of coefficients. That means at least one of them is non-zero. That's what we mean here. So, and that's, you can show that that's exactly the same thing as saying that if they're dependent, if a set of vectors is dependent, it says that one of them is a linear combination of the others, right? And so in many contexts, we'll see that something being a linear combination of the others means that somehow it's redundant, okay? So that's that would be the concept. And so if a set of vectors is dependent, it means it's like redundant, because at least one of them you could express as a linear combination of the others. Of course, that depends on the application, but that's the idea. Okay, and the way, now the correct way to say it is the set of n vectors is linearly dependent, right? Because a set is in English, it's not plural, it's singular, and so you say it is linearly dependent. Now people get sloppy, and not that sloppy to tell you the truth. This is just standard sort of mathematical convention. But what people do is they say A1 through AK are linearly dependent. And you have to be very careful, because that's just the way people say it, and it's technically not quite right. Okay, that's fine. So let's look at some examples. Well, if I have a set that consists of a single vector, oh, by the way, doesn't hurt you to know this, a set with one element is called a singleton. So this is a set of vectors. There's only one, and it's A1. So when is that linearly dependent? Well, the question is, when can I make a linear combination of one entry, 0, with a non-zero coefficient? Well, that's only if A1 is 0, in which case I can take any beta I like. Here's one, beta 1, in that case equals 2, there, okay? So 2 times 0 is 0. Okay, so basically for a singleton, for a single vector, linear dependence is like being 0, okay? So, okay, if I have two, if they're linearly dependent, so the set with two entries, A1 and A2, is linearly dependent only if one of them is a multiple of the other, okay? And so that means actually they lie on the same line, roughly speaking, okay? So that's what that means. Now, for more than two vectors, there's no simple to state condition, right? Like I can't tell you that for 4 vectors, they're dependent if blah, blah, blah. It's complicated. We will see later an algorithm that will take a set of vectors and will process them and tell you in the end if they're linearly dependent or not. So we'll be able to check that, but it's a computational thing. It's not something you can do, okay, by just looking at it. I mean, it depends, right? Okay. So let's look at some examples. There's three vectors, A1, A2, and A3. And it turns out, in this case, here's a linear combination with non-zero coefficients. The coefficients are 1, 2, and minus 3. And you can check that A1 plus 2A2 minus 3A3 is 0. There. So that means these vectors are linearly dependent, right? Or to say it very precisely, this set of three vectors is linearly dependent. Okay, and what this says is you can express, in this case, you can express any of these vectors as a linear combination of the others. So for example, let's express A2 as a linear combination of A1 and A3. Well, here, A2, what I do is I take this equation, this equation, and I put A3 and A1 on the other side, and I divide by 2, and I get this expression here, right? So, and in this case, I can also express A1 as a linear combination of A2 and A3, and I can express A3 as a linear combination of A1 and A2. Okay, so that's what it means. It simply means these are dependent, and one of the vectors, in this case all three, can be expressed as linear combinations of the others. Okay. Now, in some applications, a linear dependence, has a meaning, and it also may have a different name. So, for example, if you have cash flows, if your vectors represent cash flows of investments or something like that, or some kind of investment, or some, it could be a loan or a bond payment. It doesn't matter. A mortgage. So these are cash flows, and there, when one of those cash flows is a linear combination of the others, in finance, people would say you have replicated that cash flow. I don't remember if you remember, like a long time ago, we looked at you can replicate a 2-period loan, as a linear. You can represent as a linear combination of two 1-period loans. So then you would say that you have replicated the 2-period loan cash flow. Okay, so in different areas, specific applications, there'll be other names for linear dependence. Okay, but right now I should also just fully admit that this should look abstract, weird, and utterly uninteresting to you. If that's what you're thinking right now, then that's fully justified. So hopefully that won't be the case in a couple of weeks, or certainly by the time we finish the book, this should be natural to you and stuff like that. But for now, right now you're looking at this and saying, like, who could care less? And all I want to say is that's a perfectly good question. Okay, now if a set of vectors is not linearly dependent, they are linearly independent. So, and that's actually the concept we really need, is linear independence. And so a set of n vectors here is linearly independent if it's not linearly dependent. And so what that means is this. It says, one way to say it is this, it says that if you have a linear combination of those vectors and you get 0, right? So if you can make 0 with a linear combination, the only way to do that is if all the betas are 0, right? For any vectors at all, if I make a linear combination with all 0 coefficients, I get 0. So I can always make a linear combination 0. I just take all the betas to be 0. The question is whether or not I can do it with non-zero coefficients. And so, and that says that if the set of vectors is linearly independent, I can't do it. The only way to have a linear combination come up to 0 is that all the coefficients are 0. Okay. And again, here people say, the vectors are linearly independent instead of the set of vectors is linearly independent. But by the way, if you're around fancy mathematicians and if you are being careful and you say this set of vectors is linearly independent, they'll smile. They're not that emotive. But anyway, I'm just saying that your status will go up. Maybe you won't be able to tell, but it will go up. Okay. All right. And basically that says that not one of these vectors can be represented as a linear combination of the others. That's another way to say it. So here's an example. Let's take the n unit n vectors. They are linearly independent. How do you know that? Well, you ask yourself, if I had a linear combination of the unit vectors and it was 0, well, then you can quickly figure out all the coefficients have to be 0, and that's what it means to be linearly independent. Okay. This will be the first hint that this might be a useful concept. It's quite interesting. Here it is. Suppose you have a vector x, and suppose I tell you it is a linear combination of some vectors a1 through ak. And let's suppose those vectors, or that set of vectors, to say it precisely, is linearly independent. So that means that x is beta 1 A1 plus up to beta K AK. Okay, that's what it means to be a linear combination. So here's what's cool about it. In this case, the way you'd say it in math is you'd say the coefficients beta 1 up to beta K are unique. And what that means is this. If suppose X had a representation as a different representation. So here I've written X as a linear combination with a set of coefficients gamma 1 up through gamma K. Then what we're saying is, if that's true, the only way that's true is if gamma 1 is beta 1, gamma 2 is beta 2, and gamma K is beta K. So what's cool, what this means is that we don't know how to do it yet, but we will later. But it says that in principle, you can deduce the coefficients from the vector. So I'll say this is weird, but it says you can actually decompose. If X is a linear combination of some linearly independent vectors, I can actually discover in principle, I can discover those coefficients. There's only one way to do it. That's actually super interesting. And later in the class, you'll see exactly how to do that. But for now, and all you need is the concept of linear independence to argue that you can do this. Okay, now why would that be? Well, suppose X has that expansion. It's a linear combination with the betas, but it's also a linear combination with the gammas. So what I'm going to do is I am going to subtract this from that. And here's what I'm going to get. I'm going to get beta 1 minus gamma 1 times A1 up to this. And that's going to be 0 because the right-hand side is going to be X minus X. This is 0 over here. Okay. Now, you look at this and you realize, like, wow, this is a linear combination of A1 up to AK. The coefficients are beta 1 minus gamma 1 up to beta K minus gamma K, and you get 0. But if they're linearly independent, what it says is if you have a linear combination that gets you 0, then all the coefficients have to be 0. And that means that all of these numbers, beta 1 minus gamma 1, all the way up to beta K minus gamma K, they're all 0. And that just means that the betas are the gammas. Okay? So that's called, it has a unique representation as a linear combination. Okay, or another way to say it is, in principle, if something is a linear combination, there's only one way it's a linear combination. Not only that, but we can actually deduce what those coefficients are. In principle, we don't know a way to do it yet, but we will later. Okay, this leads us to something that's a super important concept. Again, for now, it's abstract, but we're going to be using these things throughout the rest of the book, so might as well get used to it. Just consider this your introduction. So, and it's the concept of basis. We start with a very, some people call it fundamental. Some people actually call it the fundamental theorem of linear algebra or something. I don't know. That's overblown. It is, and it's not even that hard to show. If you look in the book, I'm not going to show it, but if you look in the book, it's like a 2/3 or half a page proof of this. But much less important than the proof is actually just what it says. And here's what it says. It's very simple. It says, if you have a linearly independent set of n vectors, you could have at most n of them. Another way to say it is this. If you have n plus 1 or more n vectors, they are linearly dependent. Okay? So that's, and it's not obvious, but it's actually kind of true. It's interesting, right? So it says that if I have 12 10 vectors, then I absolutely guarantee you one of those, at least one, I can write as a linear combination of the others. Okay, so, or I could say they are linearly dependent. Okay, that's how that works, and it's actually kind of interesting, right? Okay, so that's it, and that's called the independence dimension inequality, right? Because basically it says that a set of linearly independent vectors if they're n vectors, that set can never be bigger, can never have more than n elements in it. That's what it means. Okay, so right now this is totally abstract, but that's okay. Okay, now this gets us to basis. If I have a set of n linearly independent n vectors, that's A1 through A1, that's called a basis. This is like completely universal standard mathematical notation. Okay. So what it says then is any n vector, say B, can be expressed as a linear combination of them. Okay? For some beta 1 up to beta n. And not only that, but those coefficients are unique. There's no other way you can do that. That follows from linear independence. Now, this formula here in that context, when A1 up to AN is a basis, that's called the expansion of B in the A1 dot 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 AN basis. Okay? So, expansion kind of makes sense that we're taking B here and we're kind of writing it as a linear combination, and the old world 19th century term for that is it's the expansion in the AI basis. Okay, so here's an example. This is completely pedantic and silly because it's completely obvious, but here's an example. E1 up to En, those are the standard unit vectors. That's a basis. And here's the expansion of a vector in the unit vector basis. This is silly. It says B is B1 E1 plus up to Bn En. Well, we already know that, and plus it's completely obvious, right? So, but it's just an example of a basis and an expansion in a basis. Okay. Next topic is orthonormal vectors. We'll talk about that's also going to play a big role in actually the rest of the material in the book. So, and we'll say what they are. So a set of vectors, A1 through AK, are said to be mutually orthogonal, or just orthogonal, if any pair of them, they has to be distinct, right, are orthogonal, right? So this says that AI, that if you recall this little symbol here, which is, by the way, sometimes read in English as perp, for perpendicular. This says that AI is perpendicular to AJ. And remember, that's one of the ways we say orthogonal. And of course, all this means is that the inner product of AI and AJ is 0. That's all that means. So that's what it means. A set of vectors is called normalized if they have length 1, right? So it just means they're normalized. They're not like some of them are big and some are small. They're all the same size. In fact, specifically size 1. Okay? Then they're called normalized. And a set of vectors is called orthonormal if both hold. So what that means is two things. It means that any pair of them, any distinct pair, right? You can't have I equal to J. Any distinct pair of the vectors has an angle of 90 degrees. That's number one. They're orthogonal. And number two, each of vector has a norm or length of 1. Okay, so that's orthonormal. And you can write that just in terms of the inner products. What it says is a set of vectors is orthonormal if the following is true. If I take an inner product of the ith vector with the jth vector, I get either 1 if I equals j, because the inner product of a vector with itself is its norm squared. And if it's normalized, that's 1 squared, which is 1. On the other hand, if I is not equal to j, AI, the inner product of AI and AJ is 0, and that expresses the fact that they are orthogonal. Okay, so what it is, it's a way to say that the inner products between the entries, have very simple and very specific they're very specific and simple numbers. Okay. Now, we're going to see later that orthonormal sets of vectors are linearly independent. And that's a quick calculation. We're going to see much more about it later. In fact, what we're going to find out is you can actually get the coefficient. You can actually say what the coefficients are in an expansion. And obviously, by the independence dimension inequality, you can't have more than n orthonormal n vectors. You can have n, but you can't have more. And when k is equal to n, so I have n vectors, and they are orthonormal, they're called an orthonormal basis. That's the idea. And this is very, very common across lots of fields of applied mathematics and other areas. Okay, so let's look at some examples. Well, we've already seen this. The standard unit vectors, they have norm 1. Each one has norm 1 because the sum of the squares of the entries of each of these is 1, because all entries are 0, 1 is 1, square 1, okay, you get it. So they all have norm 1, they're normalized. And they're also orthogonal. If I take any two unit vectors for different I and j, then inner product of EI and EJ is 0 because the ones are in the different positions and everything else is 0. Okay, here's an example of an orthonormal basis for three-dimensional vectors. And here they are. It's the first vector is 0, 0, minus 1. It's normalized. The second one is 1 over square root 2, 1, 1, 0. Okay, let's check. Let's take the norm of that in our head, or let's take this. So you put the 1 over square root 2 inside, right? And you square it. So you square the first entry is going to be a half, 0. Add up the sum of the squares, you get 1. Take the square root of that, you get 1. So it's also normalized. And here's our third one. It looks like that. Okay, and you can also check it is normalized. Let's just audit a few inner products just for fun. Well, let's do the inner product of this guy and that one. Well, what you can see is when you take the pairwise products, this is 0 here, so that first entry is 0, then that's 0, and that's 0, so it's 0. How about these two? These two here. Let's do that. Well, I multiply this one and this one, and I get 1. If you like, we could add the 1 over square root 2, so I would get a half, okay, in the first entry. In the next one, I get minus a half. And in the last one, I get 0. And I add these up, and I get 0. So they are orthogonal. These two vectors are orthogonal. Visually, here's two vectors, and they are orthonormal. I mean, I'm assuming here the length of that is 1, right? And the length of that is 1. But that's what it means. It means they both have length 1, and that's the origin, and they have 90-degree angle between them. So this is what an orthonormal basis looks like. It's easy to. You can also visualize an orthonormal basis in 3 dimensions. You cannot visualize it in 10 dimensions, right? You can pretend to, but you're lying basically. So if you're around people who don't know anymore, you can actually impress them incredibly. You just say, well, look, you know what this looks like here. There's 2 orthonormal things, 3 things. You can make a little hand thing and kind of get your fingers in the approximately orthonormal, and then you could say, okay, well, the same thing, only just in 10 dimensions. That's not that hard. Anyway, of course, people can't really visualize that. Okay. This brings us to the concept of an orthonormal expansion. So suppose I have an orthonormal basis, A1 through AN. Then it says the following. We have for any n vector x, I can write it this way. Now, we knew because it was a basis, we could write it as a linear combination of A1 through AN. We knew that. But now we're going to be super specific about what the coefficients are. They are, in fact, the inner product of A1 and x, all the way up to the inner product of AN and x. So this is what we call the orthonormal expansion of x, in some orthonormal basis. Okay, now, if you want to check this formula, let's do the following. Let's just take the inner product. Let's just write, we know that x must have the form, because it's a basis, it's got to have the form that looks like this, like that. Okay, so we know it's oh God, what have I done? Okay, here we go. There's A, those are A's. My mistake. Okay, so we know that because it's a basis, any vector x is a linear combination, but we don't know the coefficients beta I. Okay, so let's take the inner product of left and right hand sides of this equality with, let's say, A1, and it's going to be similar for the others. So on the left, I get the inner product of A1 and x, and on the left, I get the inner product of beta 1, A1, and A1. That's beta 1 times the inner product of A1 and A1. But these are orthonormal, so that's 1. Okay? Now, how about the inner product of A1 and the second term, which is beta 2, A2? Well, that's beta 2. If I take the inner product like that, I can put this inside and I get A1, the inner product of A1 and A2 like that. And this is 0 by normality. By orthogonality, right? So that's 0. And so all the other terms here are 0. And you just get beta. So it says A1 transpose X is beta 1, right? So that tells us that beta 1 is A1 transpose X. So that's the calculation. It's pretty simple. Again, at the moment, this should be completely abstract and weird. I mean, you may have seen it in another class. Or I don't know the context, right? But you may have seen this in another class. But if you haven't, and this looks like it's weird and abstract and has no particular interest to you, that's a perfectly normal feeling to have.